Folks, so in this video we are going to go through a second version of this coupled oscillator problem. We have a coupled oscillator, and it's very similar like the last coupled oscillator problem, but the only difference between this one and the one before is that we're going to be dealing with two different K constants. So in this coupled oscillator problem, we have the system is set up almost identically. The only difference is we have two different K constants in these springs. Here we have what we're going to call K1. Likewise, on the right, this spring is going to also be K1. But in the middle, we're going to have K2. And the question is, what are the oscillating modes of this system? Right, so we're expecting to have some omega. There may be 1 or 2 omega. It's actually, well, I'll just tell you that it's going to be two different values of omega. So we're going to have two different values, omega 1, omega 2. What are these equal to? This is the two different modes, mode 1 and mode 2, of this particular system. And this is what we're going to solve. And so to get started, we are going to once again invoke, as we did in the previous example, both f equals ma as well as f is equal to minus kx. And as you saw in the previous example, we have agreed that we can actually equate these two together to come up with our differential equation that essentially defines the modes of this problem. So both the eigenvalues and eigenenergies, but the eigenenergy in this case we're going to label as omega. So you have m times d squared dx1, where x1 once again is the displacement of this mass in the positive direction, and x2 is the displacement of this mass in the positive direction. So this is our x1s and x2s. I talked about that in the last video. dt squared. And so this is essentially our f is equal to ma of this particular mass, right? So we have the f is equal to ma, f equals ma of this mass, and we're going to set that equal to this kx, which is effectively the force applied on this mass as a result of any sort of displacement x1. So if I displace this mass any value of x1, what is going to be the force of this, the restoring force of this, due to the springs on the left and the right? And well, the answer to that is effectively minus k1 x1. So this is the restoring force of this mass due to this spring here, And I can actually just color code these if I want. I can say, well, it's going to be minus k1x, and I can say plus, and then we have the mass on the right, or the spring on the right, and the contribution to that is going to be x1 minus x2 minus x1. So this here, we can agree that clearly as you have displacement toward the right, you have a restoring force of this in the negative direction. So this is the reason why we have this minus, the reason why we have this minus x1 here. Right, because we have displacement in the negative direction. So here we have minus k1 minus k2 of x1. So if we multiply these together, we have effectively a negative restoring force, because as you displace this to the right of x1, we have a positive or a negative force due to this spring onto this mass in that direction. Right? However, if I displace this x1 to the right, clearly this mass will also move a value of x2. And if this moves a value of x2, then we have to essentially take the difference of this to find out precisely what the force of the spring onto this mass is. So now that that's clear, the next equation here is essentially doing what we did here onto the second mass. So we have m times d2x2 over dt squared is equal to, and here we have the value of minus k1 x2, again the same exact argument. You displace it, and this k1 here, or actually perhaps I should give this another color here, right? Minus k1 x2, right? We have displacement or a force in this direction as this is displaced to the right a value of x2. And we have plus, and going back to this blue color here, we have a minus, or we have k2 x1 minus x2, which of course we can also write as minus k2 x2 minus x1. All right, so the same line of argumentation here. And we did, in the previous video, we essentially took these concepts here, or these two equations, and we formed a linear equation. And we're going to do the same thing in this example here. So we're going to form a linear equation where we essentially combine these two equations here, and it makes it look a lot neater, and it actually allows us to solve for the eigenvalues of this particular problem. So we have minus k1 plus k2 over m. Then we have k2 over m. We have k2 over m here. And then we have k1 plus k2 over m. This is going to be equal to x1, x2, which of course is all equal to d2 x1 over dt squared and d2 x2 over dt squared. So, whoops. So we have these values here, and we, of course, if you aren't convinced of this, this is simply, you have this term here multiplied by this term here, plus this term here multiplied by this term here. And that would be equal to d2x1 over dt squared. And so the m's, of course, we got by dividing this over to this side. So you have over m in each and every one of these terms. And by rearranging these terms, you can see how you get minus k1 plus x2 and k2. So this should be straightforward given the previous example. And so moving on from this, we ask the question, well, what kind of a solution do we have for this particular differential equation? And the answer is that the general solution, a typical form of this solution, a typical form of a solution is given as follows. You can essentially say that a general form of this solution is equal to a times the exponential I omega t. And you can convince yourself of this by simply substituting this x for these terms here. And what this gives us is effectively, if we were to take this value here, what this would effectively give us is d2 x over dt squared. So here I would just substitute the general solution for x. You would get d2 over dt squared of a times the exponential of I omega t, right? So far so good. And of course this would all be equal to minus omega squared a times the exponential of I omega t. Of course we know this is equal to x because we just defined that, and so we have minus omega squared times x. So the story is that d2x over dt squared is equal to minus omega squared times x. And so this is an eigenvalue problem here. And so going back to the other form here, this particular solution here, going back to this here, we can say that we can effectively say that our matrix equation takes on the following form. So we have minus k1 plus k2 and I'll explain to you what I did in a second. I can do k2 here, or sorry about that, I forgot, over m plus omega squared plus, sorry about that. So you have minus k1 plus k2 all over m, and then we have k2 over m, k2 over m minus k1 plus k2 over m. This is just x1, x2, and this is all, and I'm going to give I'm going to effectively set these equal to minus omega squared times x1 and minus omega squared times x2, right? So here I simply substituted this form of the equation, right? Because originally we had d2x over dt squared. And so we can actually move these over to the right-hand side. And you can rewrite the equation as follows. You can say, well, you have k1, k2 plus omega squared, k2 over m, k2 over m, and likewise k1, k2 over m plus omega squared, x1, x2, and this is all equal to 0. So I effectively subtracted this over, the minuses turned into pluses, and I was left with this expression here, this matrix expression. And so I can actually multiply this entire, just to make this a little simple, I can multiply this entire matrix by m and effectively get rid of, because I can multiply both sides by m, this just turns into 0. And these terms cancel out, and but we have to multiply this omega squared by m, right? And so if we set a new value lambda equal to m omega squared, we can simplify this down to minus k1 plus k2 plus lambda k2 k2 minus k1 plus k2 plus lambda. And this can effectively give us what we're looking for here. we have this term here, so I'm trying to cram this all in. And so we're almost done. So if we take those two terms, if we take the determinant of this equation here, we can take the determinant of that and come up with this. We have minus k1 plus k2 plus lambda squared minus k2 squared, and set this all equal to 0. So that's just the definition of the determinant. And so we have minus k1, k2 plus lambda is equal to all squared is equal to k2 squared. Take the roots of both sides, and we're left with minus k1. I'm going to substitute the minus in there. Get minus k1 minus k2 plus lambda is equal to k2. And this is actually equal to plus or minus k2 because we are taking the square root of k2 squared, and so k2 can be negative or positive, it doesn't matter. And so we have to note that this can be positive or negative. So that's important. And so what are we left off? What are we left off with? We're having lambda is equal to plus or minus k2 plus k2 plus k1. And so we have a lambda 1 and a lambda 2 corresponding to the plus and minus here. So the first lambda 1 is equal to effectively the k2's cancel out, and you're just left with k1. And the second lambda and the lambda 2 is equal to the sum of k2, so we have 2k2, or that's not 1, 2k2 plus k1. And recalling that our lambda was equal to m times omega squared, we have m omega squared is equal to k1. And we have m, and we're going to call this omega 1, or omega 1. And here we're going to have m omega 2 squared equals 2k2 plus k1. Solving for omega and for the both omegas, and we have omega 1 is equal to the square root of k1 over m, and omega 2 is equal to the square root of 2k2 plus k1 over m. And this, folks, is your answer. You have omega 1 is equal to the square root of k1 over m, and omega 2 is equal to 2k2 plus k1 over m. And so we know that because k2 is obviously just always a positive number, k2 is a positive number, omega 2 will always be greater than omega 1. And we saw an instance like this, something very similar in the first example, where one of the omegas was a faster, oscillated at a much faster frequency, or not a much faster, but like by a factor of the square root of 3. And here we have this summation of 2k2. So this is, greater. This actual omega 2 has the summation in the radical of 2 times k2. And it is that factor by which the omega 2 supersedes omega 1 in angular frequency. And so I hope this problem clears up sort of how to solve for problems similar to these, and I hope it further elucidates the utility of invoking the Newton's second law together with Hooke's law in problems such as the coupled oscillator. And so that concludes this lecture, and I will see you in the next one.